Hey guys, today we're going to look at limits that involve some sort of infinity, either as x is approaching infinity or if the limit is going to equal to infinity. Now these limits we use to explain that there are vertical and or horizontal asymptotes. So let's go ahead and start looking at vertical asymptotes. Now when you look at this particular graph, we have 2x plus 1 over x minus 3 as our function. Remember that we have a vertical asymptote when the denominator is equal to 0. So if I take the x minus 3 and make it equal to 0, we would have to add the 3, so there is a vertical asymptote at x is equal to 3 because of the denominator. If you look here on the graph, we can see, even though we don't physically see the asymptote, we can draw it in, and we see that our graph splits there at x is equal to 3. So if I try to find these limits, the limit as x approaches 3 from the left, as you can see, goes down forever, so negative infinity. And the limit as x approaches 3 from the right is going up, so positive infinity. These are the limits that we would prove that there is a vertical asymptote. Now let's look at horizontal asymptotes. We'll get into the technique on how to find horizontal asymptotes algebraically from the equation, but we can see here that we have a vertical asymptote at this line, which is y is equal to 2. So our graphs at the ends are leveling out at 2. So if I were to try to find the limit as x is approaching negative infinity, which is the left side of my graph, this equals to 2. And the limit as x is approaching positive infinity of f of x on the right side also equals to 2. So these are the limits that we would use to prove that there's a horizontal asymptote. So to kind of put this together, we have infinite limits and limits at infinity, which can be confusing with their names, but basically an infinite limit is when your one-sided limits are going to equal to some sort of infinity. And if that's the case, then that means that we have a vertical asymptote where x is approaching that number. So we have here x is approaching c, whatever number that is from the left or right, would either equal to infinity or negative infinity. Now, it should make sense that this is what we use to prove vertical asymptotes, because vertical asymptotes are always written as x equals to whatever the number is. So if x is approaching a number and we get infinity and negative infinity, that's our vertical asymptote. Then we have our limits at infinity, which is where x is approaching infinity or negative infinity. So these are the limits that we use to describe end behavior. And horizontal asymptotes do exactly that. They affect the end behavior of the graph, because then our graph cannot go up or down forever, but level out at the horizontal asymptote. So if you have one of these limits that equals to a real number, then that means that we have a horizontal asymptote at y is equal to that number. Now, last thing is important to note that in order to prove vertical or horizontal asymptotes, you don't need to state both limits, you just need to state one of these limits. As long as one of these limits is true, then we have a vertical or a horizontal asymptote. So now let's try these out. We're going to find these limits. For this first one, we have the limit as x is approaching 2 from the left. So I'm going to go ahead and take this function, and we're going to need to factor it. So in the numerator, I notice that I can divide all of my terms by 2, so I'm going to take out a 2, and I would get x squared minus x minus 6. The denominator is x squared minus 4, which is a difference of squares, so x plus 2, x minus 2. Now, I didn't mention this before I started, but the whole reason why we're doing this is because if you just plug in the 2, then you would get 0 in the denominator. So we want to be able to factor it. So that way maybe that problematic factor will cancel and we'll be able to find that limit. So I need to continue factoring, so we're going to factor that numerator completely. So we have the 2. X squared minus x minus 6 can be factored as x minus 3, x plus 2, over x plus 2, x minus 2. So we can cancel out these x plus 2's. So now what I have is the limit as x is approaching 2 from the left of 2x minus 3 over x minus 2. Now, if I plug in 2, I still end up with 0 in the denominator. That must mean that we have a vertical asymptote. So we're going to plug in a number slightly to the left of 2. So I'm going to plug in 1.9. So 2 times 1.9 minus 3 over 1.9 minus 2. Now recall that we're doing this because since we know that this is a vertical asymptote, then that means that my answer is going to be either positive or negative infinity. So we need to know which one that is. So we're trying to test for the signs. So the 2 here is a positive number. 1.9 minus 3 is negative over 1.9 minus 2, which is negative. What we end up with is a positive times a negative, which is negative, divided by a negative would give me positive, so my answer would be positive infinity. Now before we go to this next one here, what this does is this limit proves the existence of a vertical asymptote. And we would say, when we're proving it, that there is a vertical asymptote at x is equal to 2 because, and then now here we would state the limit. So the limit as x is approaching 2 from the left of 2x squared minus 2x minus 12 over x squared minus 4 is equal to infinity. Let's try that again with this one here. We have the limit as x is approaching negative 1 from the right. So we want to factor this entire function because if I plug in negative 1, I would have 0 in the denominator. So if I factor the numerator, x squared minus 3x plus 2 can be factored as x minus 2, x minus 1 over 2 times x plus 1. Now nothing canceled here. So we're going to have to just plug in the negative 1 from the right. So we're going to, again, because negative 1 is a vertical asymptote, since that would still give me 0 in the denominator, we're going to plug in a number slightly to the right of negative 1. So I'm going to plug in negative 0.9. So we would get negative 0.9 minus 2 times negative 0.9 minus 1 over 2 times negative 0.9 plus 1. So now we need to take note of the signs. Negative 0.9 minus 2 is negative. Negative 0.9 minus 1 is negative. The 2 is positive, and negative 0.9 plus 1 is positive. So we end up with a negative times a negative, which is a positive, over a positive, which is infinity. So what this means is that there is a vertical asymptote at x is equal to negative 1 because, and now we restate the limit. The limit as x is approaching negative 1 from the right of x squared minus 3x plus 2 over 2x plus 2 is equal to infinity. Now again, when I'm restating my limit, I have to write out my original function since it wasn't named anything. If it was named f of x, I can replace that with f of x, but it wasn't. So we have to state that limit. Okay, now let's try this one out. So here, what we're going to do is we're going to find any vertical asymptotes that may exist, and we're going to justify the answer using limits. So in the numerator, I have 2x squared plus 7x plus 3 over x squared minus 2x minus 8. So we're going to need to factor this completely so that we can cancel whatever we can cancel and see what's left in the denominator to establish that that's where you have the vertical asymptote. So I have here on the side some steps that we can follow. The first step, like as I stated, is to factor the rational function completely. Now if you look in the numerator, we have a 2 in front of the x squared that I cannot factor out because 7 and 3 are not divisible by 2. So we're going to have to use the AC method. As a reminder, AC is when we multiply the first with the last. So 2 times 3 is 6. And then we are looking for two numbers that multiply to give us the 6 and add to give us the 7, which would be 6 and 1. And now we're going to replace b, which is 7x, with 6x plus x. So let's do that right now. So g of x is going to equal to 2x squared plus 6x plus x plus 3 over, now I'm just going to go ahead and factor this out already while I continue to do the work for the numerator. X squared minus 2x minus 8 can be factored as x minus 4, x plus 2. Now from here we can factor by grouping in the numerator. So this is going to give me 2x times x plus 3 plus, now here there's nothing in common, so I just write a 1 to remember that 1 is there, x plus 3 over x minus 4, x plus 2. Our final factored version of g of x is going to be, remember the factor that is the same, we're taking that out, which is x plus 3. And then what's left over is my second factor, which would be the 2x plus 1 over x minus 4, x plus 2. Now you'll notice that nothing canceled. So that means that both of these factors represent our vertical asymptotes. So as a side note, I'm just going to write this here. We have two vertical asymptotes, which are at x is equal to 4 and negative 2. Since remember, we find these vertical asymptotes by setting these factors equal to 0. So if x minus 4 is equal to 0, we add the 4, we get positive 4. And if x plus 2 equals to 0, we subtract the 2, so negative 2. So we're going to prove that we have these vertical asymptotes, and we do that using limits. So we have to do this twice because we have two asymptotes. So we're going to do the limit as x is approaching 4. Now you can choose which side you want to do. You can do the left or you can do the right. I'm going to do one of each. So I'm going to do the left for 4. And here, see, I could put g of x, since it was named as g of x, is going to equal to, now 4 from the left, I'm going to use 3.9. So 3.9 plus 3 would give me a positive number. 2 times 3.9 plus 1 would be a positive number. 3.9 minus 4 would be negative. And 3.9 plus 2 would be positive. So this, a positive times a positive divided by a negative, would give me negative infinity. Now let's do for the other vertical asymptote. We have the limit as x is approaching negative 2. For this one, I'll do the right, so we can see one of each. Of g of x is going to equal to, so negative 2 from the right, I'm going to use negative 1.9. So negative 1.9 plus 3 is going to be positive. 2 times negative 1.9 is going to, it's going to be almost close to negative 4. Plus 1 would be negative. Negative 1.9 minus 4 would be negative, and negative 1.9 plus 2 would be positive. So we have a negative divided by a negative, which gives me positive infinity. Now that I've found my limits, I can prove that my limits exist, that my asymptotes exist using those limits. So we would state, there is a vertical asymptote. Remember that here we need to write that out. VA is not an accepted mathematical abbreviation. So I use it for my notes, but when my final answer, I'm going to write it out. There is a vertical asymptote at x is equal to 4 because, and now here we state the limit as x is approaching 4 from the left of g of x is equal to negative infinity, and there is a vertical asymptote at x is equal to -2 because the limit as x is approaching -2 from the right of g of x is equal to positive infinity. Now we're going to look at limits at infinity, which is the end behavior of our graphs. We're going to start off by looking at polynomial functions. In order to evaluate limits at infinity for polynomial functions, we need to know what the end behavior is of polynomial functions. So just so you understand my notations here, when you see n, that represents the degree of the polynomial, meaning the highest exponent that you see in the polynomial is the degree. And then an, that is the leading coefficient, meaning the number that is attached to the variable with the highest exponent. Together, this creates the leading term, and that's why this is called the leading term test, because that's the power and the coefficient of the leading term tells you what the polynomial is going to do at the ends. So if our degree is an odd number, then what that means is that the ends are going in the opposite direction. So one end will go up and the other end will go down. If the degree is an even number, both ends will go in the same direction. The easiest way to remember is that the sign of the leading coefficient will always tell you the right side of your graph. And then the exponent, whether it's even or odd, will tell you if the left side is going in the same direction as the right or in the opposite. So in this first example, if you have an odd exponent and the leading coefficient is positive. So I'm going to write like what a leading term could be for the polynomial. So this one, let's just say that our leading term is x to the 5th. Positive coefficient, meaning the right side is going up. Odd exponent, left side going in the opposite direction. So the limit as x approaches negative infinity, which is the left, is negative infinity. And the limit as x approaches positive infinity, which is the right, is positive infinity. Now, same thing, if you have an odd exponent, but now my leading coefficient is negative, so let's say negative x to the 5th, that means that because this is negative, the right side is going down, so the limit as x approaches infinity is negative infinity. And then the left side, because of the odd exponent, is going in the opposite direction, so positive infinity. Now, even exponents are kind of easier because both ends are going to go in the same direction as the sign of the leading coefficient. So if you have an even exponent, let's just say x to the 4th, and my leading coefficient is positive, that means that both ends of the graph are going to go up. And if n is even, but the leading coefficient is negative, so let's just say negative x to the 4th, that means that both sides of our ends are going to go down. So let's try and work out a couple of polynomial questions. So as a reminder, the sign of the leading coefficient will tell you the right side of the graph. If the exponent of the leading term is odd, the left side will go in the opposite direction. And if the exponent of the leading term is even, the left side will go in the same direction. So always want to identify what is your leading term. In this polynomial, my leading term is 2x to the 4th. So I look at the sign. Since it is positive, the right side will go up. Since my exponent is even, the left side will also go up. So the limit as x is approaching infinity is going to equal to, and this is talking about the right arrow, which is up. Now in this example, it's not written in standard polynomial form, but we can still figure out what is the leading term by taking all of the x's and multiply them together. So my leading term, this is negative x, and it's being squared, times another x, times another x. Negative x squared becomes positive x squared, times x, which is x to the 3rd, times x, which is x to the 4th. So again, here I have my positive coefficient, so the right side will go up, even exponent, so my left side will also go up. The limit as x is approaching negative infinity, that is the left arrow, is going to equal to positive infinity since it's going up. For this one here, we have the limit as x is approaching negative infinity of this polynomial function. My leading term is going to be the 2x to the fifth. So typically your leading term is in the front, but regardless, you still want to scan your polynomial and make sure that you pick out the leading term that has the highest exponent. So because my coefficient is positive, that means the right side will go up. Because the exponent is an odd number, the left side will go down. Since this is as x is approaching negative infinity, that means that we're talking about the left arrow. So the answer here is going to be negative infinity. Last one here, my leading term, again, the one with the highest exponent, which is the negative 3x to the third. Since it is a negative leading coefficient, that means the right side will go down. And because we have an odd exponent, that means that the left side is going up. So this is for as x is approaching positive infinity, meaning the right arrow. So my answer here is going to be infinity. Now, what happens when we're trying to find the limits at infinity of rational functions? Now for these, we are going to just look at the graphs, but there is a steps to follow that we do this algebraically. So let's go over how we're going to do this algebraically, and then we'll verify our answer using the graphs. So what it says here, the first step is to divide every term in both the numerator and the denominator by the highest power of x that appears in the denominator. So let's do that first. So I look at my denominator, which is x squared, that's my highest exponent, and I'm going to divide every single term in my rational function by x squared. So x over x squared plus 2 over x squared over x squared over x squared plus 5x over x squared plus 6 over x squared. Now we simplify. X over x squared is 1 over x plus 2 over x squared over 1 plus 5 over x squared plus 6 over x squared. So that's step 1. Now we're going to plug in infinity. Anything divided by infinity will equal to 0. Now this is the case because if I have, let's say for example, if I plug in 1 over infinity for 1 over x, this is a really, really large number, right? Or I mean, it's infinity, right? So 1 divided by some super duper large number is going to be 0.00000 something something something. So basically, this is going to equal to 0. So anytime you have a number over infinity, that's just 0. So this 1 over infinity is 0, plus 2 over infinity is 0, over 1, plus 5 over infinity squared, 0, plus 6 over infinity squared, 0. So what we end up with is 0 over 1. So here, what we end up with for this limit is equal to 0. And if you look at the graph, we can see that we have the horizontal asymptote at y is equal to 0. Now let's try this one. I see here that the highest exponent in my denominator is x squared. So I'm going to divide everything by x squared. So we get 2x squared over x squared plus 7x over x squared plus 6 over x squared over x squared over x squared plus 5x over x squared plus 6 over x squared. Now we simplify. 2x squared over x squared is 2 plus 7 over x plus 6 over x squared over 1 plus 5 over x plus 6 over x squared. So that was the step one. Now we're going to plug in infinity and make sure that we write any zeros where zeros would apply. So this is 2 plus 7 over infinity, which is 0, plus 6 over infinity squared, which is 0, over 1, plus 5 over infinity, 0, plus 6 over infinity squared, 0. So what we have in the numerator is 2 over 1. So this answer is 2. And if you look at the graph, I know it's very small, but we have a horizontal asymptote at y is equal to 2. Last one here, we have the limit as x is approaching infinity of this rational function. The highest exponent of x in the denominator is x. So we're going to divide everything here by x. So we get x squared over x plus 3x over x plus 2 over x. I don't know why there's an extra positive. Over x minus 1 over x. So now let's simplify. X squared over x is x plus 3 plus 2 over x over 1 minus 1 over x. Now we're going to plug in infinity. So we have infinity plus 3 plus 2 over infinity, which is 0, over 1 minus 1 over infinity, which is 0. So here in the numerator, we have infinity plus 3, which is just going to be infinity, over 1. So this is going to equal to infinity. And if you look as the limit as x is approaching infinity, you see that there's no horizontal asymptote, and my graph is going to go up forever. Now this isn't to say that there aren't shortcuts. However, this, if you're doing an FRQ, they would require to see this method. Now for shortcuts, in case you have multiple choice questions. If the degree of the numerator, what you're doing to find the horizontal asymptotes is you're comparing the degree of the numerator with the degree of the denominator. If the degrees of the numerator and the denominator are equal, such as here, you see how the degree is 1 and the degree here is 1. What we do is we take the coefficients that are attached to that leading term in the numerator and the denominator, and we divide. This is 2 over 1, so this limit would equal to 2. Over here, if the degree of the numerator is higher than the degree of the denominator, then that means that there is no horizontal asymptote. So your answer would be infinity, or possibly negative infinity, and we'll get to that. If the degree of the numerator is smaller, see here how it's 1, and the degree of the denominator is 2, then that means that we always have a horizontal asymptote at 0. So now, let's try this out. If this was an FRQ, you would find these limits using the steps that we talked about in the previous example. However, if this was a multiple choice question, you can use the shortcuts that we used in the previous slide. So we'll do one using the proper method, and then we'll do the other using our shortcuts. So for this one, let's just do the shortcut. We have the limit as x is approaching infinity. Now, if you look, the highest degree in the numerator is the squared. So this is the negative 2x squared. This is my leading term. And in the denominator is 3x squared. So these have the same degree. So what we're going to do is we are going to divide those coefficients. So negative 2 over 3 would be negative 2 over 3. So we would say this limit will prove the existence of a horizontal asymptote. And we would write there is a horizontal asymptote at y is equal to negative 2 over 3 because, and then we would state our limit. The limit as x is approaching infinity of 5 minus 2x minus 2x squared over 3x squared plus 2x minus 3 is equal to negative 2/3. Remember that horizontal asymptotes exist if the limit at either infinity or negative infinity approach a real number. And if that's the case, that's where you have the horizontal asymptote. Now let's use the previous method the proper method of finding the horizontal asymptote for this question. We look at the highest degree of the denominator, which is the x, and we're going to divide every single term by x. So x squared over x plus 3x over x minus 4 over x, all over x minus 5 over x. Now we simplify. X squared over x is x plus 3 minus 4 over x over 1 minus 5 over x. Now we're going to plug in infinity. So infinity plus 3 minus 0 over 1 minus 0. Infinity plus 3 is infinity over 1. So we get here that this limit is equal to infinity. Since this is infinity, that means that there is no horizontal asymptote. And again, if you're using your shortcuts, if you look at the degree of the numerator, which is 2, the degree of the numerator is higher than the degree of the denominator, meaning horizontal asymptote, no horizontal asymptote. So we would say there is no horizontal asymptote at, oh, not at anything. So there is no horizontal asymptote because the limit as x is approaching infinity of x squared plus 3x minus 4 over x minus 5 equals to infinity. Now let's go ahead and have a look at how we would put all of this together. So for these two equations, we're going to find the equations of the vertical and horizontal asymptotes, and then we're going to justify the answer using limits. So let's start with vertical asymptotes. If we have a vertical asymptote, that means that when I factor everything, whatever does not cancel out in the denominator will be what I would use to find the vertical asymptote. So let's do that. We're going to factor that numerator, which I noticed that I can first take out a 2. And I would get x squared minus 7x minus 8 over x squared plus 2x minus 8 can be factored as x plus 4, x minus 2. Now let's continue factoring that numerator. F of x is going to equal to 2 times x squared minus 7x minus 8 can be factored as x minus 8, x plus 1 over x plus 4, x minus 2. Since nothing canceled out here, that means that we have two vertical asymptotes, which would be where the denominator is equal to 0. So we have 2 at x is equal to negative 4 and positive 2. So now before I write my statement saying that I have vertical asymptotes, I'm going to find the limits that would justify those asymptotes. So the limit as x is approaching, let's do negative 4 from the left. Remember, you only need to use one of the limits. So either from the left or from the right is up to you. So if I'm doing from the left, I'm going to plug in a number slightly to the left of negative 4. So I'm going to use negative 4.1. So this would be 2 times negative 4.1 minus 8 times negative 4.1 plus 1 over negative 4.1 plus 4 times negative 4.1 minus 2. And now we're just going to note the signs. Negative 4.1 minus 8 would be a negative. Negative 4.1 plus 1 would be negative. Over negative 4.1 plus 4 would be negative. And negative 4.1 minus 2 is also negative. So everything here is negative. A negative times a negative is positive over another positive would give me the answer to this limit as being infinity. Now we're going to do the next vertical asymptote. So the limit as x is approaching 2 from, let's do the right this time. Since I already did the left here, I'm going to do the right. of f of x is going to equal to 2 times, I'm going to do 2.1 minus 8 times, 2.1 plus 1 over 2.1 plus 4 times 2.1 minus 2. And now again, we're going to take note of the signs. 2.1 minus 8 will be negative. 2.1 plus 1 is positive. 2.1 plus 4, positive. And 2.1 minus 2, positive. A negative times a positive is negative over a positive, so my answer here would be negative infinity. So we have two vertical asymptotes, so we have to write two statements justifying that. There is a vertical asymptote at x is equal to negative 4 because the limit as x is approaching negative 4 from the left of f of x is equal to infinity. Oops, and I put 8. Just kidding. Is equal to infinity. There we go. And at x is equal to negative 2 because, and now we write that limit, sorry, positive 2, not negative 2, because the limit as x is approaching 2 from the right of f of x is equal to negative infinity. Now we need to determine our horizontal asymptotes. Now, if this was an FRQ, we would go through that process that we did before, where we would divide everything by the highest degree of the denominator and then simplify. But I'm just trying to save space here, so we're going to use those shortcuts. The highest degree of the numerator is the 2x squared, and in the denominator is x squared. Since they're the same, that means that we divide those coefficients. So we have a horizontal asymptote. There is a horizontal asymptote at y is equal to 2, and now we would state the limit, because now you can choose whichever limit you want to provide as proof, because regardless, the limit as x is approaching positive infinity or negative infinity when you have an asymptote will be the same. So the limit as x is approaching, let's do infinity, of f of x would equal to 2. Now let's do this next one here. We have g of x is equal to x to the third plus 3x squared minus 10x over 2x squared plus 10x minus 28. So let's factor. In the numerator, we can take out an x from each term, which would give me x squared plus 3x minus 10. Over in the denominator, we can take out a 2, which would give me x squared plus 5x minus 14. Let's continue factoring that. We get g of x is equal to x. X squared plus 3x minus 10 can be factored as x plus 5 times x minus 2 over 2 times x squared plus 5x minus 14 is x plus 7, x minus 2. So now my x minus 2's cancel, and g of x is x times x plus 5 over 2 times x plus 7. So this means that we have a vertical asymptote at x is equal to negative 7. So I'm going to go ahead and find my limit that is going to prove this vertical asymptote exists. So let's do the limit as x is approaching negative 7. Let's do the right of g of x. A number slightly to the right of negative 7 would be negative 6.9. So I'm going to plug that in for every x here. That would be negative 6.9 times negative 6.9 plus 5 over 2 times negative 6.9 plus 7. In the numerator, we have this negative. negative 6.9 plus 5 would be negative, over the 2 is positive, so that's fine, and negative 6.9 plus 7, which is positive. A negative times a negative is a positive over positive would give me an answer of positive infinity. So we would state there is a vertical asymptote at x is equal to negative 7 because the limit as x is approaching negative 7 from the right of g of x is equal to infinity. Now for our horizontal asymptote. We can use the shortcuts or we can do the long method. Let's do the long method since we did the shortcuts here. The highest degree of the denominator is x squared, so I'm going to divide every single term by x squared. So x to the third over x squared plus 3x squared over x squared minus 10x over x squared all over 2x squared over x squared plus 10x over x squared minus 28 over x squared. Now we simplify. X cubed over x squared is x plus 3 minus 10 over x over 2 plus 10 over x minus 28 over x squared. Now we're going to go ahead and plug in infinity. So infinity plus 3, negative 10 over infinity would be minus 0, over 2 plus 10 over infinity is 0, minus 28 over infinity squared is 0. So we end up with infinity plus 3 minus 0, 2 plus 0 minus 0. So infinity would be my answer. So now this, since I plugged in infinity, this means that I use the limit as x is approaching positive infinity. If I had plugged in negative infinity, then it would be the limit as x is approaching negative infinity. However, to not complicate life, right, we only need one limit to solve for the horizontal asymptotes. So I always just use infinity because it's the easier of the two to plug in. Because when you do negative infinity, then you have to take account the signs, etc. So this just works fine. So since my answer here is infinity, right, because we have infinity plus 3, which is infinity, divided by 2, who cares? It's still infinity. This means that there is no horizontal asymptote. And we would state that the reason is because the limit as x is approaching infinity of g of x is equal to infinity. Remember, if there's a horizontal asymptote, this limit would equal to a real number. Now, let's see what would happen if our limits are approaching negative infinity. So we can do the long way of figuring out what our answer is going to be, or we can use our shortcuts. Or as another method I put here as another shortcut, you may also take the leading term of the numerator and denominator and plug in infinity and evaluate using what you know about even and odd functions. So let's try that out, because most of the time these are more multiple choice type questions. So we want to be able to do these quickly and efficiently. So a shortcut would be taking whatever infinity it is and plugging it into the highest degree of the numerator with the highest degree of the denominator. So this would be 2 negative infinity squared over negative infinity squared, which these two things are the same, that will cancel. So this would equal to 2. And again, as our shortcut, right, remember when the degree of the numerator is the same as the degree of the denominator, we have a horizontal asymptote when we divide those coefficients. So we can, whether x is approaching positive infinity or negative infinity, that does not matter. The only times that we have to worry about the limit as x is approaching negative infinity is if we do not have a horizontal asymptote. If we do, my answer will be the horizontal asymptote. So as you can see, x is approaching negative infinity, the left, it does equal to 2. Now let's look at this one. As you notice, the degree of the numerator is larger than the degree of the denominator. So we are not going to have a horizontal asymptote. So we need to evaluate which infinity this is going to be, whether it's positive or negative. Now, I'm going to do this a long way so you can see how that would work. And then I'm going to show you the shortcut that I mentioned earlier. So the highest degree of the denominator is x. So I'm going to divide everything in my function by x. So this would be x squared over x plus 3x over x plus 2 over x, all over x minus 1 over x. Now we simplify. X squared over x is x plus 3 plus 2 over x, all over 1 minus 1 over x. Now instead of plugging in infinity, we're plugging in negative infinity. So this is going to equal to negative infinity plus 3 plus 2 divided by negative infinity would still give you 0 over 1 minus 1 over negative infinity is still 0. Negative infinity plus 3 is still going to be negative infinity over 1. So my answer is negative infinity. And if you look at the graph, you see that we end up with negative infinity towards the left. The shortcut that I'm talking about is taking the highest degree of the numerator and dividing it by the highest degree of the denominator after we plug in negative infinity. So negative infinity squared over negative infinity. When you square negative infinity, that's going to be positive infinity over negative infinity. Infinity over infinity, it's infinity regardless. What we're trying to check is the sign. If we have a positive divided by a negative, that's going to equal to negative infinity. So again, we would get the same answer and in a much faster way. Now, looking at this particular rational function, this is both a rational and a radical function. And the difference here is that you'll notice we have two horizontal asymptotes, where one side is approaching one number and the other side is approaching another number. So only when you have this particular function type, where you have a radical and a rational combined, you have to worry because there may be more than one horizontal asymptote. So our limits as x is approaching negative infinity and positive infinity would be different because of those two asymptotes. So for example, the limit as x is approaching negative infinity, that's the left side of my graph, is negative 2. And the limit as x is approaching positive infinity, that's the right side of my graph, is positive 2. So how would we know which one our limit would equal to? So we're going to still apply that long version. Unfortunately, that's the only way of figuring it out for these kinds of questions. We have to divide everything by the highest degree of the denominator. So we've done that before. But now here in the denominator, we have these radicals. And I have here as a note, okay? You will note that the square root of x squared is the highest degree of the denominator. When you simplify, you get the square root of x squared, which is plus or minus x. Because remember, anytime you square root, it's always plus or minus. So how do I know what to divide? It depends on what infinity it's approaching. So for example, the limit as x is approaching negative infinity, that's the left side of my graph. So we are going to divide everything in the numerator by negative x. So I always just make a note that the square root of x squared is going to equal to negative x as long as x is less than 0, meaning the left side of my graph. So let's work out this kind of problem. We're going to do 2x over negative x minus 2 over negative x over. Now this is still inside of the square root. So when we're inside the square root, we are going to divide by x squared. Because it didn't come out yet, we're still inside, which inside is x squared. Plus 1 over x squared. Now we simplify. 2x over negative x is negative 2. Negative 2 over negative x will be plus 2 over x. Over the square root of 1 plus 1 over x squared. Now we're going to go ahead and plug in negative infinity. So negative 2 plus 2 over negative infinity, which is still 0, over the square root of 1 plus 1 over negative infinity, which would be 0. So now let's work this out. We get negative 2 plus 0 is negative 2 over the square root of 1, which is 1. So this gives me negative 2. And as we saw in the previous example, because this is the previous example, the limit as x approaches negative infinity of that function is negative 2. Now let's do the next one. Now this is for when x is approaching positive infinity. So that means that the square root of x squared, which is the leading term in the denominator, is going to equal to positive x as long as x is greater than 0, meaning the positive side. So we're going to divide everything in the numerator by x. And then in the denominator, we keep the x squared since it's still inside of the square root. So x squared over x squared plus 1 over x squared. Let's simplify. 2x over x is 2 minus 2 over x over the square root of 1 plus 1 over x squared. Now we plug in the infinity. So this would be 2 minus 0 over the square root of 1 plus 0. And when we work this out, 2 minus 0 is 2 over 1, which is equal to 2. And again, this matches what we got for the right side of the graph, which is 2. Let's try that again in this particular question. We have the limit as x is approaching negative infinity of 3x minus 2 over the square root of 2x squared plus 1. So first of all, this is for as x is approaching negative infinity. So I'm going to use the square root of x squared is going to equal to negative x because x is less than 0, because we're looking at the left side. So let's divide everything in the numerator by negative x. And in the denominator, since it's still inside the square root, we divide by x squared. Now let's simplify. 3x over negative x is negative 3 plus 2 over x over the square root of 2 plus 1 over x squared. So we have, now we plug in the negative infinity. So we got negative 3 plus 2 over infinity, which is 0, over the square root of 2 plus 1 over infinity, which is 0. And this is going to give me negative 3 over the square root of 2. There's nothing else that I can do here. This is my answer to that limit. So now to answer the question, what does this say about the presence of horizontal asymptotes? We would say there is a horizontal asymptote at y is equal to negative 3 over the square root of 2 because, and now we state our limit. The limit as x is approaching negative infinity of 3x minus 2 over the square root of 2x squared plus 1 is equal to negative 3 over the square root of 2. Now, if you notice, if we were doing a multiple choice question, we don't need to go through all of this. The highest degree of the numerator is 1. And this is actually also 1 because the square root is an exponent of 1/2. So if you do the square root of 2x squared, that would give us x square root of 2. So, because I could take out the x since the square root of x squared is x. So we would still end up with the same answer, but just keeping in mind that it would have to be negative because of the plus or minus, and it's the left side. So that's another way, but honestly, if you do this, you will get the right answer every time versus trying to do a shortcut that maybe you may not understand yet, or it may be kind of like you have to think through it a little bit more. Now let's do this last one here, the limit as x is approaching negative infinity of x squared plus 2x over the square root of 3x squared plus 2. So this is for the left side. So that means that the highest degree in the denominator is the 3x squared, but it's the square root of x squared. And I'm going to use negative x because this is for when x is less than 0. So we're going to divide everything in the numerator by negative x. Now remember, inside of the radical, we keep it as x squared. Now let's simplify. X squared over negative x is negative x. 2x over negative x will be negative 2 over the square root of 3 plus 2 over x squared. Now we're going to plug in negative infinity. When we plug in negative infinity, it will be negative infinity minus 2 over the square root of 3 plus 2 over negative infinity squared, which would still be 0. Negative infinity would be positive infinity. Minus 2 is still positive infinity. And over the square root of 3 is still positive infinity. So positive infinity. So what we would say here, since this is not a real number, is that there is no horizontal asymptote because the limit as x is approaching negative infinity of x squared plus 2x over the square root of 3x squared plus 2 is equal to infinity. And that's limits and infinity.